start the last session. So it's a pleasure to have Furong Huang, and you see Irvine, but I guess now you're postdoc at Microsoft.
Right.
And she's going to give a talk on spatial dictionary learning.
Thanks, Ross, for introduction. So I'm Furong. Today I'm going to talk about spatial dictionary learning using tensor factorization. This is joint work with my PhD advisor, Nima and Kuma. So I guess there's no need to motivate in this audience that feature learning is the cornerstone of machine learning, right? So in computer vision, you have this multi-layer, multi-resolutional representations of the images, which are really the key to success. And in natural language processing, we're able to map human languages such as words or even phrases into vectors in vector spaces so that the machines will understand what the languages are talking about. Okay? So what's really important in these kind of things are really, we wanted to find an efficient representation of data based on some structure of the data, say sparsity or low rank representation or group invariances and so on. So here comes the natural question. So is there a principled approach so that we can have guaranteed learning of good representations, right? So this seems to be a very vague statement. What do I mean by good representation? So dictionary learning actually is a concretely defined problem that aims to find good set of representations. So I guess all of us are familiar with this linear dictionary learning problem. It's just we assume the existence of dictionary elements, say A, and then the columns of the A are just the dictionary elements. Then we posit that the signals are generated through a linear combination of dictionary elements, right? So then the goal is really to find the hidden dictionary that are common to all the samples and to find the feature representation for each sample. So these feature representations are really sample specific. Now there seems to be a good problem set up, but there is a problem. Say in images, right? So look at this example of 3 images. So the dictionary learning model would naturally think the first and second pair of images are closer than the first and the third pair, simply because these 2 shapes are in the same location. But if you ask a human, then we might, based on a common sense, we think the first and the third pair are actually closer, because both of these images are just a figure of balls, right? So what's missing really here is this invariant dictionary models or invariant dictionary elements that we are able to, that humans are really good at finding out, but not necessary for this traditional dictionary learning model. So, but now let's say we tell the machine that, look, for a concise representation, you should use the ball or and the star as the dictionary elements, but we still wanted to find the locations of the dictionary, right? So basically, those will be essential for our representations of the images to distinguish between different images, okay? So what we really want here is actually a spatial dictionary learning model that's able to have like shift invariant dictionaries and location encoded representations. So convolution model actually naturally incorporates both of these requirements. Then formally the model assumes that the generative model is the signal is generated through linear combinations of convolutions through filters and activation maps. So these are the filters and these are activation maps. Okay? So this actually is a simplified version of 1-layer convolution neural net. So usually what would you do? You do alternating minimization, so some gradient-based method. However, usually these methods have this non-convex landscape, and you might oftentimes stuck in spheric's local optimal, right? So what's even worse in this case is that you have this additional symmetry, which means the shifted version of the filters are oftentimes also the solution to your problem, right? So sometimes this can be also computational prohibitive because you ended up usually iterate over a large number of samples in each iteration. But let's take a closer look at the model, right? So if actually there is a nice thing that we observe that this convolution between the filters and the activation map can be reformulated as just the multiplication of a circular matrix of the filter multiplied with the activation map. So just to recall you, a circular matrix is just a square matrix whose columns are just the filter itself and the shifted versions of the filters. Okay? So just to write this summation into vector form, you get this stacked circulant matrix multiplied with also the stacked super long activation vector. Now this seems like, okay, are we done? It seems like this is just a dictionary learning problem, and we can just use dictionary learning techniques. But how do we do dictionary learning, right? So a few years ago, Alan Kuma et al. Brought this old and good inverse Massimo moment back to our attention. So basically what they're saying is using some conditional independence given coefficients, we're able to relate the data moments with the model parameters. So what do I mean here? Say we have a pairwise data moment correlation matrix, and then this matrix actually can be written as just a bilinear operation over the pairwise data moments over the hidden variable or the coefficients, right? So this becomes like a core matrix and then these operations. In some special case, this core matrix becomes just the diagonal thing, then you can have this nice eigenvalue decomposition. Then you might argue, okay, let's do just eigenvalue decomposition on this matrix, and then we can get these columns of A, which are basically the elements, right, the dictionary elements. But the claim is that matrix decomposition only recovers the subspace, not the actual model. You need to go one level up and look at the triple-wise data moments, I guess. But why is that, right? A simple idea is by looking at maybe matrix orthogonal decomposition. And we know that if there's no eigenvalue gap, then there is no unique decomposition, even for orthogonal matrix decomposition. So this is an example. So you have an identity matrix. Then the identity matrix can be decomposed as the eigenvectors. Any rotation of this basis vector are also going to be an eigenvector of this identity matrix. So that's because there is no eigenvalue gap. Okay? But for tensor, this actually becomes very nice, which says that if you have an orthogonal decomposition for a tensor, then even if you don't have eigenvalue gap, this decomposition is going to be unique. And what's even nicer is that you can just think about slicing the tensor. And then what's nice about the slices of the tensor is that they can be simultaneously diagonizable, and they also share the same eigenvectors as the tensor have. And now, based on how you slice the tensor, you can actually get some eigenvalue gap, right? Then you can uniquely identify the eigenvectors. Okay, so now we know that the orthogonal tensor decomposition is unique. Then what we can do is become fairly simple. You look at the dictionary elements, columns of A, and then you wanted to find a projection such that you project these elements of columns of A to orthogonal bases, right? So like this. Of course, you can find many such W's, but you can just find your favorite one, and you project data with W. Now, your projected triple-wise data moment becomes something like that. It will have now an orthogonal decomposition form. And since we said that tensor orthogonal decomposition is unique, then you can uniquely identify these components, these red and blue and yellow ones. Okay? Of course, you can then project it back to the space because you did some projection of W, but you know what projection you did. You can then just do W inverse to revert it back. So
question?
Yeah.
So you're not using anything about convolution yet? Or?
Not yet. So we're only talking about the dictionary learning. So That's undercomplete. That's correct. So in a nutshell, what we've talked about now is, tensor decomposition uniquely identifies the dictionary elements up to some permutation as long as the dictionary elements are linearly independent. And the computation can be really efficient. If you do dimensionality reduction or sketching techniques, you can implement this really fast. And the sample complexity can also be quite reasonable. But now, what we really want is, like Sanjeev is saying, we wanted to do spatial dictionary learning models, right? So it seems like there are some difficulties there. First, if you don't consider this circulant structure, this seems like an over-complete dictionary learning problem, because the number of the columns of the stacked circulant matrix is greater than the data dimension, right? And also, as I said before, there are some additional symmetries about the problem. Essentially, the shifted versions, so this dark blue dots are essentially, all of them are shifted version of some filter, and all of them are global optimal of this problem. However, we do observe some nice properties for this specific application. First is this circulant matrix is actually a simultaneous diagonalizable group. What do I mean by that? So for any same size circulant matrix, they can be simultaneously diagonalized by Fourier transform matrix. And you know exactly what the form of the Fourier transform matrix is. And then the diagonal elements are just the Fourier transform of those filters. So this seems to be a very nice property that you can use in your algorithm. Another observation is this circulant projection. So for any square matrix, you wanted to find its closest circulant projection or circulant matrix. And it turns out you have a closed form solution for that. So in the interest of time, I won't go into the details, but the takeaway message is that you can just efficiently find such a closest circular matrix. Now, with this in mind, it seems like suggesting us that, okay, you can just do a tensor decomposition with some circulant projection, right? So naively, what you would do is, I don't know, think about the naive loss function, like just the reconstruction error on your cumulant or your triple-wise data moments. Now, of course, these Fs are circulant, stacked circulant matrices, and this lambda is just the diagonal matrix. So what you wanted to do is, in practice, we know that alternating least square is very efficient. Then we wanted to kind of do this asymmetric relaxation and kind of fix the two modes of the tensor and update the third mode. Okay? So if you do that, this becomes a really simple least squares problem. And we know that as long as this gigantic matrix is full rank, we are able to compute the unconstrained solution for this problem. So T is not yet a circulant matrix. But then we can just compute them. We can just project them into the circulant space. And in this case, it's actually a blocked stacked circulant matrix. Okay, so we know the closed form update solution for that. But what's the problem here? The problem is that, as I said before, there is this pseudo inverse over this gigantic matrix. And if you do it naively, actually it will take O(n) to the 6th time. N is the filter length. Right, so not only it is very computationally expensive, but also you might end up getting a lot of instability doing this gigantic matrix inversion. Okay, so note that, as I said before, these circular matrices have this very nice simultaneous diagonalizable property. Then we can just use them to drastically reduce the complexity of the algorithm. So I'm not going into the details of this, but essentially what we need to do is just a bunch of FFTs, some matrix multiplication, and inverse of some diagonal matrices, which are all very cheap operations. So if we do that, then we can get a very nice running time if we fully utilize the degree of parallelism in this algorithm. Essentially, the running time is just the logarithm in the filter length and the number of filters. Okay, so I also wanted to compare with the alternating minimization about the running time. So the first row is just time per iteration if there is no parallelism. And you can see that tensor method seems to work pretty good when the number of samples is large. There's a lot of samples. But now if you fully utilize your computation power and you exploit the maximum degree of parallelism, then the running time for tensor per iteration seems to be better than the alternating minimization, even if you do stochastic alternating minimization, which is n equals to 0. Oh, n equals to 1, sorry. Okay. So some synthetic experiment results. So we kind of can, because there is a generative model underneath, we can do some synthetic experiments. You can just have your ground truth filters, and you can just generate your data based on your spatial dictionary learning model. And what you can do is to compute, for tensor the results from the tensor decomposition, the results from the alternating minimization, and trying to compare the reconstruction error of the signal, and also directly compute the errors between filters. Right, so in this case, there are 2 filters, and you can see the dotted lines are just for AM, and the solid lines for convolutional tensor. Seems like we're doing better in terms of both the reconstruction error and the direct error on filters. Okay, so also, if you think about the running time, these 2 plots suggest that this tensor method scales much better when you increase the number of filters and you increase the number of samples.
Sorry, I must be something obvious. So by alternating minimization, you mean doing alternating minimization in the original space?
Oh, right. So alternating minimization, what I really mean is like just do gradient, like alternate between the filter and the activation maps for each samples. So you then have to like kind of calculate that for all the samples, right? So in summary, what I talk a little bit about method moments for learning dictionary elements. So there are some guarantees for uniquely identification of the dictionary elements, and therefore you are guaranteed to learn a good representation of the data. Also, we talked about how to deal with invariances in dictionary models, right? And also, how can we do it efficiently using less time and maybe make the algorithm more robust? And looking into the future, I'm thinking about some extending this framework into broader families of invariants, say rotation invariances, scaling invariances, which are all common in images, right? And also I'm interested in, and this is undergoing work, interested in analyzing the optimization landscape of this problem for invariant models using tensor methods. Hopefully this will help us to understand convolution neural nets better, or at least shallow convolutional neural nets better. So that concludes my talk. I'll be happy to, take some questions. Thanks.
It looks like non-convex. I'm not sure. Then does it is a convergence local or global? How does it relies on your initialization?
So are you talking about alternating minimization or?
Yeah, the problem and the algorithm. Yeah.
So we're kind of using alternating minimization as the baseline, and because this problem is essentially saying you can just naively minimize some reconstruction error directly on the signal, then this problem becomes non-convex, And of course, nobody knows what happens under these situations. What is the optimization landscape look like? Can you guarantee it to local optimal, can you guarantee to converge to local optimal point, whether your saddle points are a manifold or they are separable? Well, these kind of things are not known yet, especially under the convolutional model. And also the tensors, we still don't have a theoretical guarantee that we're converged to a global optimal yet either. But based on some previous works on tensors, we kind of have some have some ideas that this might work in this situation, and we're still working on things. Because what makes this really hard is, this Fourier transforms actually are complex numbers, right? So you have to analyze this landscape actually in a complex space, not only on the real space. Yeah.
Maybe just time for one more question, and then maybe
You can set up.
you can set up.
So have you tried there are all these tricks for optimization? For example, initialize the dictionary using samples and overparameterization?
Yeah, that's a very good point. No, we haven't tried that. But that's a very interesting question. Yeah.
So how did you initialize?
For tensors. So are you for alternating? We just do some bunch of random initialization and pick the best one.
Oh, not with samples.
No.
I see. But that would be the more natural one.
Yeah, I guess in this set experiment, we're not trying very hard to make alternating minimization work very well as people do in neural networks. We're just trying to see essentially, well, one point is we wanted to compare the running time, and other point is just that we're not tuning the tensor methods very hard, and we're also not tuning the alternating minimization very hard. Can we see whether the reconstructions, how does the reconstruction error compare?
Yeah, but I think with the alternating minimization, the standard initialization would be using samples. I mean, at least for dictionary learning.
Oh, I think that's for ALS, right? For ALS, you kind of use a SVD kind of.
No SVD, just samples, random samples.
Okay. Yeah, so I didn't try that, but that's a good point. I might wanted to try that.
That may be very different.
Okay. Yeah, thanks.
Okay, let's thank the speaker again.